In this lab, we want to find the charge on a statically charged piece of clear tape. In order to find the charge, we set up an experiment where we measure the distance that one piece of charged tape is repulsed by another piece of charged tape. We ran this same experiment in the last lab. However, when inputting our data and running the calculations to find the charge on the piece of tape, we made the simplifying assumption of treating each piece of tape as a point charge. In this lab, we will instead treat each piece of tape as composed of numerous point charges using a computational model. The lab was composed of two major parts, the experiment and creating the computational model. After completing both parts, I found the charge on one piece of tape to be 1.1 times 10 to the negative 7th coulombs. In the experiment, I used two pieces of tape, each 0.18 meters long and with a mass of 0.0018 kilograms. I set up the experiment as I did in Lab 1, using two books to lay one piece of tape on and bring the second piece of tape up from underneath. The distance that tape 2 repelled tape 1 was 5 centimeters or 0.5 meters. In order to use a computational model to find the charge on the piece of tape, using the distance I found from the experiment, I began by applying the model of a point charge to the situation. If we view each piece of tape as a line of numerous point charges, we can find the electric field that each point charge of tape 2 creates at the location of each point charge in tape 1. Summing up all of these small electric fields is made simple by using a for loop that can brute force all of the calculations. After finding the electric field made by tape 2 at each particle in tape 1, we can find the force at each of these points by multiplying the electric field by the charge of the particle, and then finally sum up all of these forces to find the total force. This total force should be equal to the force that gravity exerts on tape 1, being the mass of the tape multiplied by the acceleration of gravity, or in this case, 0.017658 newtons. We can use this program to solve for the total charge in the tape by plugging in different hypothetical charges and comparing the force that the code outputs to the value of the Fg that we calculated. The goal is to find a value of the charge that results in an output that is pretty close to the correct force of gravity. Though this program is more realistic than considering each piece of tape as a point charge, it still simplifies the situation by considering each piece of tape as a thin line of point charges rather than a rectangular array of point charges. It also makes the same assumption in Lab 1 that each piece of tape has equal charge. Comparing the results from Lab 2, the charge being 1.1 times 10 to the negative 7th coulombs, to Lab 1, in which I found the charge to be 7 times 10 to the negative 8th coulombs, the numbers are pretty close, but the results from Lab 2 should be more accurate since the model was closer to reality. These results show that the charge on the tape is in actuality slightly larger than if you view the tape as a point charge. This makes sense when you compare the equations of the electric field of a point charge to the electric field of a thin rod. The electric field of a thin rod will be slightly less for a point charge, given the same total charge and R values.